Hello and welcome to the Math 200 lecture for this week. We're going to be covering Chapter 8, which is about sampling distributions. So just a quick overview of what we've done previously and how it relates to the stuff that we're doing this week. So previously we learned about random variables and their probability distributions. We talked about discrete random variables like the binomial distribution, and what we did is we found probabilities using formulas, tables, and StatCrunch. We also learned about continuous probability distributions like the normal distribution, and we found the areas under the normal density curve using a combination of z-scores and then looking up the values on the table or using StatCrunch. So now what we're going to do is we're going to continue to discuss probability distributions, but statistics like the sample mean and the sample proportion are going to be the random variables. So let's think about it like this. So if you want to find average income of all US households, we can't survey everyone. That's only done every 10 years as part of the census. It's very time consuming, very costly. So what we can do is we can take a random sample in order to estimate the average income. And we could take more than one sample. Every time we take a sample, we're going to get a slightly different mean, since different households would be selected in each of the samples. And because of this, the sample mean is a random variable, so it has to have a probability distribution. So those are the probability distributions that we're going to be looking at this week. So let's start with section 8.1, which talks about the distribution of the sample mean. So when you're asked to describe a distribution, we're going to talk about a couple of different things. But statistics such as x bar, that's your sample mean, are random variables since their values vary from sample to sample. Just like we talked about, if we wanted to find the average household income, if we took one sample, that mean would be different from a different sample. And as such, they have probability distributions associated with them. So in this chapter, we're going to focus on the shape, the center, and the spread of these types of statistics. So when you're asked to describe a distribution, we're asking about three different things. We're asking about the shape, which is either going to be normal or not, the center, which is going to be the mean, and then the spread, which we're going to talk about the standard deviation. So anytime you're asked to describe a distribution, those are the three things you need to include: shape, center, and spread. So the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from some sample size of n. Now, the sampling distribution of the sample mean x bar, and hopefully you've seen this notation before when we talked about sample means, I think way back in chapter 3, but x bar is just it's just your sample mean. And the sampling distribution of the sample mean is just the probability distribution of all possible values of your random variable, computed from a sample size n from a population with a given mean of mu and a given standard deviation of sigma. So let's look at an example here. So let's look at something where we have a sample mean for some kind of normal population. So the weights of pennies minted after 1982 are approximately normally distributed. The mean is 2.46 grams and standard deviation is 0.02 grams. And we want to approximate the sampling distribution of the sample mean by obtaining 200 different simple random samples, all of size 5, from the population. So what we would do for this is we would go ahead and select 5 pennies, okay, at random. And here's an example of what the first sample might be. So maybe we got a penny that weighs 2.493 grams, and then the next one weighed this much. So we now have a sample of 5. And what we do is we do this 200 different times. So for this particular sample, the mean, our x bar, our sample mean, was 2.479. And then this same kind of process was repeated 199 more times. And these were the results that were obtained. So that 2.479 is all the way up here, and then they recorded all 200. Now this was done using some kind of simulation technique. But basically what they did, each of these observations represents the sample mean for 5 different pennies that were weighed. So they took 5 pennies, they weighed them, they took the average, they recorded it. Took 5 more pennies, weighed them, took the average, recorded that. So it's not individual observations, they're already summarized. So the mean of the 200 sample means is 2.46, which is the same mean as the population. This is what we would expect to have happen. The standard deviation of the sample means is 0.0086, which is quite a bit smaller than the standard deviation of the population. And we're going to talk about, we have an actual formula for calculating standard deviation here that's pretty easy to use, and we'll talk about how sample size affects that in just a few minutes. But the next slide shows the histogram of the sample means. So here we have, it looks like we had almost 40 different samples of 5 that had a weight in this category here. It's kind of hard to tell what it is because not all of these little pieces are labeled. But it's pretty nicely bell-shaped, looks pretty normally distributed. Now, one thing to kind of note is that as the sample size increases, the standard deviation is going to actually decrease. So that has kind of an inverse relationship there. And if you look at this example here, here's something that looks very similar, except this is the mean of 200 sample means for n equals 20. So what they did in this case is they did some kind of simulation again with the pennies. So instead of taking samples of 5, they took samples of 20. So for example, if you can imagine like a big bucket of pennies, they would have taken 20 of the pennies out, weighed them, and taken the average and recorded that. And then they would have taken 20 more pennies out, weighed them, taken the average, recorded that, and so on. And they would have done that a total of 200 times and then created this histogram. Now the mean is still the same, the mean is still 2.46, but now the standard deviation is 0.0045. And if you remember back, it was 0.0086 when we had n equals 5. So as we might expect, there's less variability in our data when n equals 20 than when n equals 5. And if you think about it, if you think about picking 5 pennies out, we could get really one penny that kind of messes up our sample a little bit. Maybe, I don't know, it's been worn down completely and it weighs much less, or it's brand new and weighs a lot. So when you only have a sample size of 5, that one penny can kind of have a large impact. But when you have a sample size of 20, chances are that one kind of outlier penny doesn't end up making a big difference. So we have formulas here for the mean and the standard deviation. So let's go through this slide and then we'll see how it actually works. So let's suppose that a simple random sample of size n is drawn from some kind of large population with a mean of mu and a standard deviation of sigma. So the mean and standard deviation are given. Now the sampling distribution of x bar, mu of x bar, that's this right here, is going to be the same as the population mean. And then we have a little formula for calculating the standard deviation. All you have to do to find the standard deviation of your sampling distribution for x bar is to take the given standard deviation of your population and divide it by the square root of n, okay? So all you do is you take the given standard deviation and divide by the square root of n. Now, this right here is also called the standard error of the mean. And it's kind of a more typical term that you'll see used. So this is the standard error of the mean, and this is just the mean of the sampling distribution. So again, we expect the means to be the same, but we expect that as n increases, our standard deviation decreases. And this right here is our formula for calculating our standard error. So if a random variable x is normally distributed, the distribution of the sample mean for x bar is also normally distributed. So let's take a look at this example here. We have the weights of our pennies again, approximately normally distributed, mean of 2.46, standard deviation of 0.02. And what we want to answer is this question here, which is what is the probability that in a simple random sample of 10 pennies, so we're going to take 10 pennies out of our bucket of pennies, we want to know what is the probability that we obtain a mean of at least 2.465 grams. So we have a couple things we need to do. The very first step is to go ahead and describe our distribution. That's something that you probably always want to take a look at. So to describe the distribution, we know we can say it's normally distributed because the weights of pennies in general are normally distributed. So x bar is normally distributed. The mean is going to be the same mean that the pennies follow in general, which is 2.46 grams. And in order to find our standard deviation, all we do is we take the given standard deviation, which was 0.02, and divide it by the square root of n. In this case, we have a sample size of 10. So we take our 0.02 and we divide it by square root of 10, and you should get 0.0063 here. So at this point, we have a mean and we have a standard deviation. Mean is just the same as it was from the population, and standard deviation we calculate by taking the population standard deviation and dividing by the square root of our sample size. Now, in order to calculate the probability, we are going to rely very heavily on topics from Chapter 7, which was our normal distribution chapter, where we go ahead and we calculate z-scores, we look the values up on the table, and so on. So if we calculated a z-score, we can do this two different ways. We can either calculate the probability using z-scores and then the table, or you can do it in StatCrunch. So let's take a look at the by hand method first. So we would calculate our z-score by taking whatever we're interested in, which was our 2.465 grams, and subtracting our mean of 2.46, and dividing by our standard deviation, which we had to recalculate using our sample size. And if you do this, you get 0.79. And then what you want to do is you want to look it up on your table. So I'm just going to minimize out of this presentation for a minute and bring up my z-score table. So I have my standard normal table here. So I'm looking for 0.79. And if I look here, I have 0.7, and then I go all the way over to 9, and I have 0.7852, it looks like. Now, if we take a look, I want the probability that we obtain a sample mean of at least 2.465 grams. So that means greater than or equal to. So anytime you're shading to the right, anytime you have that greater than, taller than, heavier than, anything like that, you have to do the 1 minus the table value. And again, this is a property back from Chapter 7. I would take a look back over z-scores from that chapter if you're still not comfortable with this. So I take 1 minus the value from my table, and I get 0.2148, or basically a 21.48% chance of obtaining a sample mean of at least 2.465 grams. Now, using StatCrunch, we can use our normal calculator. So let me minimize out of this again, and let me pop over to StatCrunch, which I have open here. And all I need to do, let me move this kind of out of the way here, is go to Stat, Calculators, Normal. So it's nothing new. This is the same stuff from Chapter 7. All I do is I enter my mean of 2.46. And my standard deviation, instead of entering the original standard deviation, I enter my new standard deviation for my sample mean, which is 0.0063. And then I want the probability that we have at least 2.465. So I'm going to select greater than or equal to 2.465 and click compute, and it gives me 0.2137. This is a little bit different. You always get slightly different answers with technology. That's not an issue. I'll accept either on quizzes that I'll hand out, so either one is fine. And my math lab deals with either type of answer as well. Okay, let's take a look at this example here where we have a non-normal population. So if you were paying close attention, the last one, we already had a normal population because we're working under the assumption that weights of pennies are already normally distributed. So let's take a look at what happens if we're dealing with a non-normal population. So the following table and histogram give the probability distribution for rolling a fair die. So we know we basically have a 1 in 6 chance of getting a 1, a 2, a 3, a 4, a 5, or a 6. They're all equally likely. So this is a distribution that would look something like this. And if we were to take the mean of this, we would get 3.5. So on average, we would expect a 3.5 to come up. Now, it doesn't really make sense because we can't get a 3.5 on a die. But if we were to take the mean of this, we would get 3.5. And the standard deviation we could calculate using our information back from Chapter 6, and we would get a standard deviation of 1.708. Now, this population distribution is not normal. Okay, that's kind of one thing to note. But if we go ahead and take a look at this example here, you'll see what actually happens. So let's estimate the sampling distribution of X bar by obtaining 200 simple random samples of size 30, and then calculating the sample mean for each of the 200 samples. And we're going to repeat that twice, once for n equals 10, once for n equals 30. I think there might be another one too, maybe 5, I don't recall. We'll see them on the next slide though. But basically what we're doing is we're rolling a die, let's say 10 times, and figuring out what the mean was for those rolls. So for example, if we got a 1, a 2, a 6, we'd add up whatever we got, we'd divide by the number of rolls, and we would get some kind of mean for those 10 rolls. And we do it again and again and again until we have 200 of those simple random samples. So if we take a look at what this looks like, here's an example of what it might look like, and this is just a simulation, okay, so this isn't something that you need to replicate, but this data was actually simulated. And these were for sample sizes of 4, okay, so basically they rolled the die 4 times, they calculated the mean, and they recorded it. Rolled it 4 times, calculated the mean, recorded it, and so on. And then here's an example for n equals 10, another simulation, and n equals 30. And what you should notice is this n equals 30, this looks, it looks like a really almost perfect bell curve here. So the mean of a sampling distribution is equal to the mean of a parent population, which we already know. And standard deviation of the sampling distribution is also going to be sigma over square root of n, regardless of sample size. But the interesting thing is the central limit theorem, which we've kind of touched on before, which basically tells us that the shape of the distribution of the sample mean becomes approximately normal as our sample size increases, regardless of the shape of the underlying distribution. So if you already have something that's normally distributed, then that's great. Your sample is going to be normally distributed, or your sampling mean is going to be normally distributed anyway. But if you have something that's not normally distributed, if you have a large enough sample size, then it's going to be normal regardless of the population size. And you can see that back here, we had something that clearly was not normal, but when we take the sample means, they do make a nice kind of normal curve. So let's look at an example here. Let's suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. So if a random sample of n equals 35 oil changes is selected, we want to go ahead and describe the sampling distribution. So we know that it's going to be approximately normally distributed, even though it doesn't tell us up here that it's normally distributed, simply because of our sample size. And I didn't mention on the last slide, there's not like a steadfast rule that always works, but one thing we'll kind of use as a nice little benchmark in this class is that if your sample size is at least 30, then you can say it's pretty normally distributed, okay? And it's always nice to put the word approximately in there because nothing's ever perfectly normally distributed, but we would say that x bar is approximately normally distributed because of the sample size. The mean we would expect is going to be 11.4, which is the same mean from your population up here. And the standard deviation is found by taking the standard deviation that was given and dividing by the square root of n, square root of your sample size of 35. And we get 0.5409 as our standard deviation there. So that is what you should do if you're asked to describe a sampling distribution. You want to talk about the shape, the center, and the spread. So shape was the normal, center was the mean, and spread was the standard deviation. Okay, so if a random sample of n equals 35 oil changes is selected, what is the probability that the average oil time change is less than 11 minutes? So if you can imagine, for example, that we take, I don't know, maybe you have a spreadsheet with all of the oil change times for the month, and we randomly select 35 of them, and we take an average of those 35. We want to know what is the probability that that average would be less than 11 minutes. So what we do is we calculate a z-score again. So we take what we're interested in, which is our 11, we subtract our mean of 11.4, and we divide by, again, our standard deviation that we calculated. And you get negative 0.74. Now I'm confident that at this point you guys can all find the probabilities. You can either use StatCrunch like I had mentioned, using the stat calculator's normal. This is the same as just exactly the same as it was a couple of slides ago, or you can use your normal tables and you can look up negative 0.74. Now, since this one wants less than, once you look it up on the table, you don't have to do any subtracting. So we just get a probability of about 0.23, so about a 23% chance that if we take a random sample of 35 oil changes, the mean oil change time would be less than 11 minutes, about a 23% chance of that happening. So this right here is kind of a nice little summary of being able to describe the distribution for your sample mean. So if the population is normal, with a mean of mu and a standard deviation of sigma, regardless of the sample size, the shape is also normal. Now the mean is just the same as the mean. Standard deviation, or standard error of the mean, is just found by taking sigma over square root of n. Now this is the same regardless, okay? But if the population is not normal, the shape is said to be approximately normal as your sample size increases. So in order to say that something is normally distributed, it has to be one of two things. Either the population has to be normal, or the population can be non-normal if you have a large enough sample size. So you have to make sure that if your population is not normal, you have a sample size of roughly at least 30. Okay, so let's take a look at section 8.2, which talks about the distribution of the sample proportion. So we're going to talk about what a population proportion is, what a sample proportion is, and soon this should all make sense here. But let's go through this definition and then we'll look at an example. So let's suppose that a random sample of size n is obtained from a population in which each individual either does or doesn't have a certain characteristic. So we could talk about blue eyes or whether or not someone approves of the president, okay? It could be really anything. Basically, kind of like success or failure type of thing. Basically, they have a characteristic or they don't, or they do something or they don't do something, or like smokers versus non-smokers, something like that. So the sample proportion, denoted p hat, okay, we read this as p hat, it's just like a p with a little hat on top, is found by taking x over n. Now x is the number of individuals in the sample that actually have the specified characteristic. So for example, if we're talking about presidential approval rating, it would be the number of people who approve of the president. And then n, of course, would be your sample size. Now the sample proportion p hat is a statistic that estimates the population proportion. So we've talked a lot about the fact that we cannot get perfect population means and population proportions simply because it's very time-consuming, very costly to ask everyone a question. So what we're going to do is we're going to use our sample proportion to estimate our population proportion. So let's look at this example here. We have a university poll conducted in May of 2008. 1,745 registered voters nationwide were asked whether they approved of the way that George W. Bush had handled the economy. And 349 people responded yes. We want to go ahead and obtain a point estimate for the proportion of registered voters who approve of the way that George W. Bush is handling the economy. So we're interested in those people who approve. So basically all we do is we take the people who approve, which would be your 349, and divide it by the total, which was your 1745, and you end up with a value of approximately 0.2, or about 20%. Now, if you want to describe a sampling distribution, we know we talk about shape, center, and spread. So as the sample size increases, the shape is going to be approximately normal for a sample proportion, just like it was for the sample mean. The mean of the sampling distribution of the sample proportion is the same as the population proportion, it's just p. And then the standard deviation of the sampling distribution decreases as the sample size increases. And we'll have a formula for that in just a minute. So this gives kind of a nice little summary right here. This is found in your 8.2 lecture notes as well. But basically what we say is that the sampling distribution of p hat is approximately normal as long as n times p times 1 minus p is at least 10. So this is something that you just need to check before you say that something is normally distributed. And on a quiz or a test, I might ask you to show your work. I don't want you to just say it's normally distributed. I want you to actually go in and say n times p times 1 minus p is 40, so it's at least 10, so we can say that it's normally distributed. If it's not at least 10, we can't really say that. Now, the mean of the sampling distribution of p hat is just basically estimated as just p, or population proportion. And in order to find the standard deviation, what you do is you take p times 1 minus p over n, and you have the square root of the whole thing. Okay, so that would be your value, or your formula for that. Pretty basic little calculation there. Now, it's also required that sampled values are independent. So when we're sampling from a finite population, meaning some kind of defined countable population, this assumption is verified by making sure that the sample size is no more than 5% of the population size. So for example, if we're talking about, let's say, 100 people, we want to make sure that our sample size wouldn't be more than 5 people. Or if we're talking about 1,000 people, it should be no more than 50. Basically, we had talked about this a little bit back in Chapter 5 when we talked about probability. But if we have a small population size, when we select an individual out of that population, it changes the population that currently exists. So if you only have 20 people to begin with, when you take someone out, you're only left with 19, and it really truly has changed your population. But if you're talking about the 318 million Americans who live in the US and you take one person out of that group, it doesn't really change the population by much because the population is so incredibly large. So when you're dealing with large populations, sample size doesn't matter quite so much. You can still have quite a large sample, but if you're talking about a small population, like if you're only interested in Math 200 students at Ivy Tech, it might be kind of a small population. You need to make sure that your sample size is no more than 5% of the population size. Okay, so let's take a look at an example where we're going ahead and we're finding probabilities, because this is kind of a typical question. So according to the CDC, 18.8% of school-aged children aged 6 to 11 years were overweight in 2004. Now, in a random sample of 90 school-aged children, we want to know what is the probability that at least 19% are overweight. And then we're going to answer the question. We're going to suppose a random sample of 90 school children resulted in 24 overweight children. We want to figure out what we could possibly conclude from that. So let's look at A first. The very first thing we want to do is we want to make sure that our assumptions are met, okay? So our sample size is 90. If you think about our population, it's all children 6 to 11. That's going to be a pretty large population. So taking only 90 individuals out of that it's definitely going to be less than 5% of our population size. And then the other thing we want to check is that n times p times 1 minus p is at least 10. So our sample size was 90. Our proportion was 0.188. That was our percent of children who were overweight. And then we do 1 minus 0.188 and we multiply those three numbers. We get 13.7. That's greater than or equal to 10, so that assumption is met as well. We can say that it's normally distributed. And then step 2 would be to find the mean and the standard deviation. Now, the mean is just going to be that population proportion that we were interested in, or our sample proportion, which is just the 0.188, or 18.8% of overweight 6 to 11-year-olds. The standard deviation we calculate using that formula, p times 1 minus p over n, and then the square root of that whole thing. And you just need to do this in your calculator really carefully. If you're having issues getting this to work out, maybe pause the video and give it a try with an extra set of parentheses. So as soon as you hit your square root key, it doesn't hurt to put an extra set of parentheses and then enter it as it exists here, and then close that extra set at the end. You should be able to get the 0.0412. So question A says in a random sample of 90 school-aged children, so we're going to go ahead and select 90 school-aged children, and we're going to calculate the proportion that are overweight. We want to find the probability that at least 19% are overweight. So if you recall from the previous slide, the mean is the 0.188, standard deviation that we calculated was 0.0412. So again, we calculate z-score just like we did before. We take what we're interested in, which is our 0.19. You always want to make sure that you're putting the percents as decimals. You subtract the mean of 0.188 and divide by the standard deviation. And make sure if you're putting this in your calculator all at once, parentheses around your numerator. And you should get 0.0485. Now, I'm hoping you guys are all super comfortable with z-scores by now. Again, you can either use your table or you could be using StatCrunch for this. If you're using your table, you're going to look up this value on the table, and then you're going to have to do 1 minus that value because you have at least 19%. So that means 19% or more. So that's a larger than question, so you're shading to the right, so you have to do 1 minus the table value. Now if you try to look up 0.0485 on the table, it only goes to 2 decimal places, so you're going to have to look at 0.05. And you'll find a value of 0.5199, and you have to do 1 minus that value, so you get 48.01%. So basically there's almost a 50% chance of finding at least 19% of school-age children being overweight in a sample of 90. All right, now let's look at this here where we have a random sample of 90 school-age children and we have results. So let's say that 90 school-age children were looked at and 24 of the 90 were overweight. We want to figure out what we might conclude. So if you think about this one, we still know our mean, we still know our standard deviation. In this case though, our p hat, that's our sample proportion, is the 24 overweight children divided by the total number in our sample. And so we got a sample proportion of 0.2667. So we want to figure out if this is kind of a rare occurrence. So what we might do is we might calculate a z-score for this. So this was the sample proportion that we obtained. And if we subtract the mean that we would expect and divide by the standard deviation, we get a z-score of 1.91. Now, the probability of getting a z-score greater than or equal to 1.91, in order to figure that out, you would look up the value on the table and do 1 minus that value again, and you get 0.028. So that's about 3%. So what that means is that if we took 100 simple random samples of size 90, we would only expect about 3 of those samples to have a proportion that was as high or higher than this. So 3 in 100, that's pretty rare. We would say that that's kind of an unusual sample to obtain if the true population proportion is 0.188. So what we might conclude is that maybe the true population proportion is not actually 0.188, or maybe we just happened to get a sample that was kind of unusual. So that's it for this week. It's a pretty short chapter this week because really what we're relying on are all things that are from Chapter 7 in terms of the calculations. The only difference is that you need to calculate a new standard deviation for your mean and a new standard deviation for your sample proportion, the standard errors, using the sample size. That's really the only difference in terms of the calculations. So let me know if you have any questions, and take a look at the lecture notes as well. Hopefully you can use a combination of StatCrunch and your normal tables to solve all of those questions.